Hello, my name is Nathan Pacey. I'm going to be going over section 15.5 of the Stewart Calculus book, looking at methods of computing surface area. To understand how we can compute surface area of a curvature in 3-space, we might want to revisit how we computed area under a curve, that is just with x and y. So we're going to go look back at Riemann sums. So to conceptualize how we compute area under a curve, we remember that we use that delta x width and the y height for the respective domain of a function. You can see figure 2 and figure 3 here. Now we've gone over this a bit in the past, so I won't spend too much time on it. But essentially, the more rectangles we create under the curve, the more accurate it will be. You can see that figure 3 here is going to be much more accurate than figure 2. So that is to be said mathematically that we can take the area under a curve as the sum of all the rectangles under it. So the sum from 1 to n number of rectangles for a function, let's say f of x, and a width of delta x. That is, if our rectangles are structured from the x-axis. And then if we're finding the area under the curve for its entire domain, we would take the limit where n approaches infinity. Now, we know that you can compute this as the integral from 0 to n. When you take the limit of the sum, you know that it's equivalent to the integral of the function. So now that we have a bit of a basis revisiting the two-dimensional areas, we can get into areas of surfaces. So let's say we have a equation, a function of two variables z that is equal to f of x and y. So we can apply the same principles. So let's call surface S, and it's continuous for all of its partial derivatives in x and y. We can take the domain of this function as a rectangle, meaning we have a respective x and y as the maximum and minima, so that will create a kind of rectangle for all of its domain. So for simplicity, we're going to be looking at the area when f of x and y is greater or equal to 0. So just like we did with the two-dimensional area under a curve, we're going to be creating rectangles tangent to our surface. So to do that, we need to figure out an equation of tangent plane that is to our surface, and we need to figure out how we can get an equation for the tangent plane small rectangles at every point. So let's dive into that. Let's say the area, again, delta x and delta y. So if we have a point xi and yi on the small rectangle that is closest to the origin, we'll call it P of I and j, the point above x and y on surface S. And this will have the coordinates you can see here of xi, yj, and f of xi and yj. So if we want to compute the tangent plane at point P, it will approximate the value of S, that is the value of the surface, when it is close to P. Further, the area under the tangent at P is approximately the surface area of S at P. So therefore, just like one variable calculus, like one variable areas, we can take the summation of all the tangents at the small tangent approximations to the surface area, and as the number of these rectangles approaches infinity, this area is approaching the actual surface area value. So you can see we have the sum of delta t. It's two summations, and we have when I starts at 1 and j starts at 1 and goes to n and m. And when m and n approach infinity, we know that this equation here will approach the actual surface area of our function. So here we can see what I was talking about with the point Pij, And in figure 4, we can see what we were talking about earlier, where we have the tangent plane with its respective vectors a and b, and the point on surface S, P of I. Now you can see the projection onto the x and y plane. That is the domain of delta x and delta y, the area in x and y. So let's take a look, because we have to further define this tangent plane in order to get a value, because we want to eventually get a value for the surface area. So using the properties of A and B, we know that the magnitude of their cross product will equal the area of delta t. That is the area of the small rectangle of the tangent plane. So this is incredibly useful because we can formulate equations for A and B, take the magnitude of their cross product. So that's what we do here. So we know that, by the way, A and B are in the x and y axes in this example. You can see that here. They're parallel to it. So since the slope of a tangent line can be described by their partial derivatives of the vectors, we can get the equation for A and B as such here, where delta xi plus the partial derivative in x for the function times delta x is our A, and likewise for B but with y. So then when we take the cross product of it, I'm not going to get into too much computation, but you can see what our resultant is here. And since delta x times delta y is our area, we can simplify it to this equation here. And then to equal delta t, we'll take the magnitude of it. That is to just use basic Pythagorean theorem and root and square each individual in I, j, and k. So now that we have a equation for delta t, we can sub that into our limit where n and m approach infinity, and we can see how we could get an approximation for the area, a surface area. And just like we did with our one variable function, we now know that we can take the double integral of the domain of delta t and sub in our newfound equation for delta t. Okay, so now we can do some application examples to further understand the relationship that we've just derived. So, say we had the surface z equals 1 plus 2x plus 3y plus 4y squared in the domain of x is greater than or equal to 1 and x is less than or equal to 4. As well, y goes from 0 to 1, and that is where it can equal 0 or 1. So we have an expression for a domain here for reference. So now, if we look back at the equation here, we know that we must first take the partial derivative of our function in both x and y. So we do that. So the partial derivative of zx is equal to 2, and the partial derivative with respect to y is 3 plus 8y. So now we have a basic equation for our surface area, where we take the magnitude of the partial derivatives plus 1. So when we do some computation, we will get that 14 plus 48y plus 64y squared, and it's all square rooted. And we know our bounds is going to be the bounds of x and y. That's our domain. So we just have to match the integration with those bounds. So we know that it's going to go from 0 to 1 in y and 1 to 4 in x. That is dy dx. So after doing an integration in y, we have the equation, the answer here. That's the first integration. And then we can do our second integration in terms of x. And we get a final expression for the surface area. Now this doesn't tell us too much because it's in terms of the natural logarithm and some not nice rational fractions. So we just take the approximation here, and you can see that it's about 22.2 units squared. I didn't get into too much computation of the integral because that's something that we've done before. And in this specific example from the textbook, it just says to use a integration calculator. So now I'm going to be doing example 2. So example 2 is find the area of the portion of a sphere, radius 4, that lies inside cylinder x squared plus y squared equals 12. So I graphed a little visualization here. We have the sphere centered at 0, 0, and we have the cylinder also centered at 0, 0, and you can see the intersection right here above the x and y plane, and that's what we want to get. So first we know that a sphere centered at 0, the origin, will have an equation as such, and we know that the parametric form of this equation will be 4 sine of psi cos of theta plus 4 sine psi sine of theta plus 4 cos of psi. This will be our parametric form equation, where the theta will go from 0 to 2 pi because we're not restricting the z-axis, the z-coordinates of our sphere. So now, since we are dealing of intersection of surfaces, we know that we have to take the equation of the sphere and input it into the equation of the cylinder to solve for z. So when we do that, we know that x plus y squared is equal to 12. So we can put that into the equation of the sphere, and we get that z squared is equal to 4. You can see a little bit of computation here. So we know that z is going to equal to plus or minus 2. But if you look back at our graph here, you know that it has to be above the x and y plane. That is, z has to be equal or greater than 0. So when we put z is equal to 2, because it can't be negative 2, back into the parametrized equation, we know that cos of psi has to be a half, which means that psi can be anywhere from 0 to pi over 3. So now that we have the bounds for theta and psi, we can now do our integration. We know the bounds of our integration. But before we do that, we need to take the relationship of the cross product of our. So using the parametrized equation, we can now take the cross product of the partial derivatives in theta and psi, and its magnitude will help us find the surface area. Because remember when we had the magnitude of cross of A and B, and we use that to find. So we can see the partial derivative in with respect to theta will be negative 4 sine psi sine of theta plus 4 sine psi cos of theta. That's a mouthful. And you can see here what the r with respect to psi will be. So then we can take the cross product of it and its magnitude. And once we have an expression for the magnitude, and it simplifies nicely to 16 sine of psi, we can put this into the double integration with our bounds we found for theta and psi. That is 0 to 2 pi and 0 to pi over 3 for psi and theta respectively. We can sub in the magnitude of the cross product of the partial derivatives, and we can find what our surface area would be. So when we do that, we sub in 16 sine of psi, we do our double integration, and we find that the surface area will be equal to 16 pi units squared. You can see the computation here for reference. So now, because it's Halloween, I wanted to do a bit of a bonus problem where we will use our skills in math to find the surface area or an expression for it of a pumpkin. So first we need to build our pumpkin using our knowledge of two-dimensional shapes. So I'm going to be using epicycloid and rotating it to create our three-dimensional pumpkin. So for a little bit of a visual of what an epicycloid is, I brought in my favorite website, and you can see the rotation of a smaller circle around a bigger circle. And this describes the equation of an epicycloid. So if we go back to lecture here, we can see that our parametrized equation will be in terms of the inner circle and outer circle's radii. So we have those equations here for x and y. And now we'll take them in 3 space to make our pumpkins. We'll now have 3 different circles of A, H, and N. And you can see what the different pumpkins will look like. And this will be what their equations are when you parameterize them. So for the bonus question, we're going to be focusing on this pumpkin here. And it's where A is 1, H is 1, and N is 10. So we want to find an expression for the surface area. So first we can sub in our values to find the parameterized equation. And just like in question 2, we will have to take the partial derivatives of the equations, and then we can take the magnitude of the cross product of our 2 partial derivatives, and then put that into the integration and find our surface area. So we do that. Unfortunately, these are very not fun because they're large equations, so we get a rather large expression for the magnitude of our cross product. And then we can input that with the bounds from 0 to 2 pi and 0 to pi. That is just because of the epicycloid. It was defined to have bounds of 0 to pi and 0 to 2 pi. So when we finally do that computation, the full expression without doing any integration will look like this. And I inputted what the pumpkin will look like in a coordinate plane. And for reference, you can see here it's rotating here thanks to this online calculator. So that is my lecture on how to compute surface areas. I hope everyone has a safe and fun Halloween. Thank you.